Here's a reaction, and hopefully it looks quite familiar. 1-bromopropane reacting with potassium hydroxide. Halogen or alkane reacting with the hydroxide. If I asked you, what would that produce? Based on what you've already learned, nucleophilic substitution reactions, I would hope you would say propanol and potassium bromide. And you wouldn't be wrong. In fact, you could well possibly be correct. However, if I add in one little bit of extra information, and this is going to be the reaction conditions, I'm going to tell you the reaction conditions are an ethanolic solvent and maybe some heat and pressure. Now, if you said you'd form propanol and potassium bromide, you would be wrong. So this reaction is the same as the one you've already studied, but we've changed the reaction conditions. And because we've changed the conditions, we're going to change entirely what happens. We're going to change what is made. Now, because we've got the same two reagents and we're going to make different products, the exam board love questions about this, because this is how they're going to test. Do you know the reaction conditions? Do you know the different reaction mechanisms? And can you really say why these reaction conditions are different? Can you predict what's going to form if you're given an equation and the conditions? So let's actually draw out what's going to happen. Some bits will be familiar, some bits won't. So we've got 1-bromopropane. First thing to do, draw the spine of 3 carbons. Draw the bromine on carbon number 1. Fill everything else out with hydrogens. So first thing you'll probably notice is whenever I did nucleophilic substitution, I always had the halogen sticking out the side if it was on carbon number 1. This time I've got it pointing down. It doesn't actually matter, but I think it makes it easier to distinguish between the two mechanisms in your head if you put the bromine in a different position, and it makes it, in my opinion, this one easier to remember. So again, we don't care if it's potassium, that's going to be a spectator ion, but we do need a hydroxide ion with the minus charge. I'm going to put the minus on the H. It is actually on the oxygen, but hey, that's fine for now. So we've drawn out our two reagents. As you probably guessed from the title, it's an elimination reaction we're going to do, rather than a substitution reaction. So in a substitution reaction, it's a 1-for-1 swap of two different things. And because it's just a 1-for-1 swap, you are going to have the same number of reagents and products because it's a 1-to-1 swap. In an elimination reaction, that's not the case. When we say elimination, we're basically saying we've got the organic molecule, the 1-bromopropane, we're going to eliminate something from it. We're going to use the potassium hydroxide to get something out of the bromopropane. We're going to eliminate something from the organic molecule. And because we're going to eliminate something from the molecule, we're basically splitting it into two different things. We're going to have more products than we have reagents. So we've got 2 reagents here. We're going to produce at least 3 products because it's an elimination reaction. And that's how you can always tell if a reaction is elimination. You'll have more products than you've got reagents. So first thing to do, as always, let's put on our partial charges. Delta minus on the halogen, a delta plus on the carbon it's bonded to. Because of the difference in electronegativity, no other partial charges. If this was a nucleophilic substitution reaction and we had an aqueous solvent, we'd have to say that the hydroxide ion attacks the delta positive carbon. It acts as a nucleophile. But in this case, it's not going to act as a nucleophile. The hydroxide is going to act as a base. Now, if you go back to GCSE, or even when you first got introduced to acids and alkalis, the first alkali you ever learn about is a hydroxide. You always learn about sodium hydroxide and potassium hydroxide and Li being the good, almost definitive bases, the definitive alkalis out there. So the fact this is a hydroxide and it's going to act like a base shouldn't really be a surprise. Now, if you think, what does a base do? It accepts a proton. And a proton is just a hydrogen plus ion. So now you've got a choice. If you look at this 1-bromopropane, there's 7 different hydrogens that the hydroxide could act like a base with and steal that hydrogen. Which one is it going to attack? So we're going to ignore everything on the carbon furthest to the left. That's basically too far away from where anything's going to happen. We don't care about that. It's nowhere near that carbon-bromine bond. And that carbon-bromine bond is the only thing that makes this different from an alkane. So that's the only thing that makes this reactive. And therefore, that's got to be part of this reaction, that carbon-bromine bond. So the carbon furthest to the left, we can ignore. It's too far away from the carbon-bromine bond, and that's where the action is going to really happen. So that means now we've only got 4 different hydrogens to attack. And what we're going to do is we're going to attack one of the hydrogens on the carbon next to the one that's attached to the halogen. So we're not going to take either of the hydrogens on the delta plus carbon. We're going to attack one of the ones on the carbon next to it. Again, it doesn't matter which one, I always do the one at the top. So we've said the hydroxide is acting like a base. We've drawn the curly arrow from the lone pair on the hydroxide to the hydrogen. Now, for the hydrogen to be accepted as a proton, so it's acting as a base, it can't take any of the electrons with it. And that means we've now got a spare bond. That carbon-hydrogen bond has 2 electrons on it, because it's a covalent bond, so it's a pair of electrons. And now it's not bonded to everything because that hydrogen has been taken off by the hydroxide to form water. So we need to do something with those electrons. We could say they just go back onto the carbon and they act like a lone pair. But then the carbon would have a negative charge. We don't really want a charge if we can avoid it. That's not that stable. We could say that the pair of electrons on that carbon go to the delta positive carbon. But that delta positive carbon already has 4 bonds, so it doesn't want to gain any more electrons. So we'll leave that in the back of our minds and just think that pair of electron has to go somewhere. Now, when we did nucleophilic substitution, we know that that carbon-bromine bond is important because the electrons in the more electronegative halogen, so the bromine, are already close to the bromine. And that means we can break that bond and the electrons can go on to the bromine. We can get rid of that bromine and it can just become a bromide. Now, that carbon, the one that was delta positive, that now has space where it can accept some electrons, or it can form a bond with something. So the electrons that were in the carbon-hydrogen bond where the hydrogen got taken off as the base, the electrons from that bond are going to form a bond between those 2 carbons. Because if you think about it, when the hydroxide took off the hydrogen, carbon number 2 was left with only 3 bonds. It could form another bond. Carbon number 1, when the bromine leaves, can also form another bond now. It has space to form another bond. So the electrons that were from that carbon-hydrogen bond are just going to form another bond between the 2 carbons. So all of this happens simultaneously, basically at the same time. It's not one thing happens after the other. But whenever I draw this mechanism, So I'll get rid of the arrows. I always think of it as falling down the stairs. So the electrons and the curly arrows you draw start at the top, go to the hydrogen, and then you fall down the stairs. So go from bond to bond, and then go from bond to bromine. And if you look at the shape that you've kind of formed at that point, disturbing, you've gone from down here, then you've gone across, and then you've gone down. So you should always form that basically stair-like pattern. It's all happening simultaneously, but when you draw the arrows, form that pattern of going down the stairs, and that's how I remember it. And that's why I always put the bromine at the bottom and the hydroxide at the top. And that also reminds you to always take the hydrogen off an adjacent carbon to the one that has the bromine on. So that's the actual mechanism. And if you think what you've formed, between those two carbons, we've now got a double bond because the electrons are moved to form a second bond. So on the carbon number 1, we're left with just 2 hydrogens, and on the other one, we're left with a hydrogen, and then we've got a CH3 group coming off this one as well. So basically what we've got now is propene, so CH3, CH3H2, propene, and we now think what else we've formed. In that first step where the hydroxide takes a proton, we've now got 2 hydrogens and an oxygen. That's water. And the potassium we're saying is a spectator ion. This bromine here, that came off as a Br minus, so we formed potassium bromide. Now, this is a very simple example of elimination reaction. Now we're going to go to a slightly different one. So this time we're going to start off with two bromobutane. And again, we're going to react it with a hydroxide ion. What are we going to form? So I'm going to draw this out again to show the mechanism. And I'm going to include both of these carbons, but the final one at the end I'm just going to write as H3C because again, it's not on one of the carbons next to the bromine, so it doesn't get involved. What could we possibly form? So, first thing to think about, let's say we attack this hydrogen here on carbon number 1. Now, that's an absolutely perfectly fair thing to do. We're allowed to do that because it's on one of the carbons next to the delta plus carbon. So if we do that, that bond's going to collapse down there, and then we're going to get the bond from the carbon bromine onto there. And what we form is, always draw the double bond. First carbon has lost one of the hydrogens, that's only got 2 now. This one's lost the bromine, so it's left with 1 hydrogen. And then we've got C with 2 hydrogens, and then a methyl group there. So what we formed there is but1ene. So that's what we could form. Now, This is why this is a more complicated example, because actually we can form more than just but1ene. Because there are two different carbons that we can attack. There are two carbons adjacent to the delta positive one that has the halogen on it. So let's say we attack a hydrogen that was attached to carbon number 3, this one here. Again, it's a perfectly acceptable one to do because it's on a carbon next to the one that has the halogen on. So again, we go from bond, from the carbon-hydrogen bond to the carbon-carbon bond, and then we're going to break the carbon-halogen bond there. So now if we draw what we've got the carbon-carbon double bond. The carbon, let's start on the left-hand carbon, that's now attached to a CH3 group and a hydrogen. And the carbon number 2, the one that did have the bromine on, is attached to a hydrogen and is also attached to a CH3 group. So what we've got here is but2ene. But it doesn't end there. If you look at the two carbons either side of the double bond, both of those carbons are attached to two different groups. And that means it can show a form of geometric isomerism, cis-trans or EZ isomers. So they're on opposite sides of each other on the carbon-carbon double bond, because carbon-carbon double bonds don't have free rotation. So it does matter whether they're pointing up or down. So this is going to be the E isomer. We've got E but2ene. And in the same way, with the exact same mechanism, just by chance, what happens if both of the methyl groups are at the top and the two hydrogen groups at the bottom? We're going to have Z but2ene. So if there's more than one adjacent carbon, and you can get different groups on the carbons at either side of the double bond, then you need to think about the different isomers that can be formed. So from 2-bromobutane plus a hydroxide, you're going to form 3 different isomers of but1ene, E but2ene, and Z but2ene. When you have branched alkanes coming off the carbon with the halogen on, then it can get even trickier. But for those ones, it's worth just having a go with them yourselves.